what was the most momentous bit of science that you heard about this year? Every December, the journal Science asks its editorial staff this very same question, and they eventually crown one discovery as their breakthrough of the year. John Travis is the managing news editor at the journal, and he took me through this year's shortlist.
Well, Science started doing a Molecule of the Year maybe 3 decades ago, and in 1996, we switched over to a Breakthrough of the Year. It's a little bit of a controversial idea because many people hate the word breakthrough in science. Science is an incremental process, but we still felt it was important to note the major developments across the scientific disciplines, particularly ones that might have an impact on society. And so we, the news editors and the editors who help select the research papers each year, get together and debate what were the top advances or discoveries. And I would say we usually start with 30 to 40 ideas and whittle it down to maybe 15 to 20, and that's when the real fight begins. It's often interesting in that the people who know a topic best aren't arguing for it, and the people who are outside of the topic are really fascinated. So it's a lively discussion, and there's often disagreement on the final choice.
And what's on the short list this year? What have you settled on as the final list of things that you think really do constitute breakthroughs?
Well, it runs the gamut from old bones to earth science. We highlighted a couple of fossils. Kennewick Man, which is a famous and controversial skeleton found in America, was tied to Native Americans by an analysis of DNA. And then in South Africa, some fossils that were found in a cave in a very unusual way. Researchers had to advertise for short, thin people who could wedge their way down into the cave, pulled out these bones, and we don't know what they are. They are apparently another hominin species, but we don't know how old they are or where they really fit into the family tree. I think one of the biggest biomedical stories of the year was a happy story, which was the development of the Ebola vaccine. Last year, science labeled the Ebola epidemic its breakdown of the year, and this year we're able to flip it over and say we may be able to prevent such outbreaks because of a new vaccine that was tested during the ongoing epidemic. The other one that fascinated me was a group engineered yeast to produce the precursors of painkillers or directly painkillers, ones that are related to morphine and the opioid family. This could be very big for medicine in developing new ones, but there were some people concerned that we could transform that yeast into producing illegal drugs, particularly people at home. I think that's pretty far off, but it is something that the community is going to have to watch.
Well, it's something we have to consider more broadly, isn't it? Because with the advent of molecular biology and all these tools that now you can buy off the internet, you can do some pretty high-level stuff in your garden shed. But moving on a step then, what's the breakthrough of the year from science this year?
So science chose CRISPR, a relatively new method of editing DNA, as its breakthrough of the year. It was a little bit of a surprise choice, I think, internally, because we had already honored CRISPR twice in 2012 and 2013 as part of our runner-ups to other breakthroughs of the year. So it's not brand new, and the spectacular success of the Pluto mission made it a very tough choice. But CRISPR produced such a wide range of accomplishments this year, many of them posing ethical and societal challenges, that we felt it was hard to deny CRISPR its moment at the top.
John Travis. So what is CRISPR and how does it work? One of the pioneers of this technology is Harvard's professor of genetics, George Church.
So the way the technique works is a scientist, or in principle a physician, will inject a molecular machine into multiple cells in your body. these machines will go through the DNA of the cell looking for a match for a particular target, and then when it finds that match by looking through 6 billion base pairs randomly, it will lock into it and will cut it. And so now it has to be repaired in order to function, and then you'll repair it with another piece of DNA that you've brought in from outside that has the exact sequence that you want to edit in. So you cut, and then you bring in and repair.
So you specify this is the sequence or combination of genetic letters I'm looking for. That targets your molecular scissors to the right place in the DNA and cuts it, and that's at the point you can bring in like a molecular sticking plaster, a new piece of DNA that repairs editing in a change in some way at the point where you've made the cut.
That's exactly right. So the breakthrough here is that is very inexpensive to build and very straightforward to get efficient and accurate replacement of DNA that you want to edit.
What sorts of things can I edit with this? If I've got someone with cystic fibrosis and I've got an egg corresponding to a baby that's going to turn into someone with cystic fibrosis, could I edit that egg to take away the cystic fibrosis gene and correct the abnormalities so that baby, when it grows up, is not going to have cystic fibrosis?
Probably the initial applications will not be at the egg stage, but there are almost any other disease. If you can get access to the cells, the tissues that are affected, then you can change them in the child or the adult.
You've recently published some work showing that this might also enable us to use, say, pig organs in humans in order to surmount the current organ shortage for transplantation. How does that work, and what were you editing there to make a pig organ usable for a human?
Right. Well, so there's millions of humans that could benefit from organ transplant, but there's not nearly enough donors. It's not just a matter of matching. And so what we can do with the pigs is we can use CRISPR to engineer so they match well, so that we can overcome the immune barrier. And also we want to make them safe, so we have engineered out the viruses that are built into the genome of every pig cell and are capable of crossing over into humans. But we've now used CRISPR to eliminate all 62 instances of these viruses that are built into the genome.
Does it make mistakes? Is there a danger that when editing the DNA, one could accidentally strike out the wrong thing or misedit, or some bit of the DNA is a better match than you thought it was and you go off target and edit the wrong thing?
So there is off target, but the best off target rates are much, much lower than the spontaneous mutation rate. So all of the cells in your body have a certain rate of mutation, and this is lower than that already, and it's improving every day. But yes, one of the things that you have to worry about with all new therapies is off target.
And how long do you think we're looking at now between it being science's breakthrough of the year and something that is being routinely deployed medically but also out there in the field to do things like combat malaria?
Well, we already have 4 organisms for which the gene drives work, including 2 malaria mosquitoes. So that could go very quickly. And we have 3 or more major companies that are dedicated to getting the gene therapies into the clinics, probably within a year or so. So I think both of those are very near future.
George Church.